Hello everyone, I'm Susendra Gulasekharan, founder of Sunamate. I'm here to talk about testing OFDMA benefits. And as you can see in the picture here, we're going to compare the performance of single user against OFDMA. Let's see which one is better. Before we get into actual testing of OFDMA, first let us understand what is the gains of OFDMA in theory, in what scenario it will happen. Secondly, what is the right metric to measure to assess whether there is gain or not. And thirdly, do we have the right tool set to make all those measurements, right? So let's start with the theory, a little bit of motivation for why OFDMA. So here is a plot of collision probability with respect to number of devices contending to transmit for Wi-Fi. So assuming you have 10 or more devices, as you can see from the plot, we are going to experience a collision probability in excess of 20%, right? And what happens in Wi-Fi whenever a collision is encountered is that three things happen. First point, there is wasted airtime. Second point, whenever there is a collision, the rate adaptation algorithm tends to react to that collision by reducing the data rate. This definitely brings down the performance further. And thirdly, there is a drain on the battery life of the client devices. So clearly, when you have a lot of clients connected to an access point, especially running uplink traffic, collisions are going to become a significant factor that determines the performance, and also it has implications on the battery life. So is OFDMA a solution? I mean, this was proposed as a solution in Wi-Fi 6, right? OFDMA. There are other solutions like target wake time as well, but today our focus is OFDMA. So what is the idea here? So if we had a lot of clients connected to an AP sending uplink traffic, the way the transmissions happen on the air is each client has to contend for the medium and then get an acknowledgement back from the AP, and then another client contends for the medium and then gets back an AP, gets back an ACK, and this goes on, right? So there is no predetermined schedule here, so every time it is basically a battle, right? So there can be collisions that happen in this sequence of events, and there will be wastage of airtime, right? So this is how the single user approach works. If we use OFDMA, the AP starts by sending a basic trigger frame, and in that basic trigger frame, the AP specifies a list of clients which can participate in a triggered uplink. So, and all those clients which have been specified in the basic trigger can respond to the basic trigger with the trigger-based PPDU, and here they can send their uplink data. And this is done using resource units or RUs, right? And since all the resource units are orthogonal, they don't interfere with each other, so all of them can be transmitted simultaneously, and then the AP can send back a multi-star block ACK, right? So this is one block ACK that aggregates the block ACK of all the clients, right? So this is clearly a much more efficient way of handling uplink traffic, right? First of all, we are not incurring the random backoff overhead every time, as in the single user case. There is a random backoff overhead for every transmission, and secondly, there is 5 header overhead in each of these PPDUs, which is also an overhead. So in the case of OFDMA, we are avoiding all those 5 header overheads, and then we are avoiding that multiple random backoff overhead. So clearly, this should have been a much efficient solution, right? But there are challenges. So here is the RU plan in the case of 80 megahertz. This is how the RU plan is described in the Wi-Fi 6 standard. So the challenges are definitely there. So first of all, there are several, I would say, not so good design aspects of OFDMA in the standard. The first among them, I would say, is this constraint of one client can be assigned only one resource unit or one multiple RU unit. So I mean, the word multiple RU gives you the impression that you can assign multiple RUs to a client, but that's not actually correct. You can assign only one MRU or RU to a client, right? So these are the RU assignment constraints that we have, right? And the AP has to work within these constraints. So remember, all these RU assignments are specified in this basic trigger frame, right? So what is the problem of having this constraint, in terms of assignment, is that it's going to complicate the scheduling algorithm, right? The complexity of the RU allocation algorithm is going to be significantly high, and whether the access point really has the memory and the compute resources to do all those calculations and computations in such a limited time, right? Because it has to decide on this RU allocation pretty much very quickly, right? Otherwise, it's going to be wasting airtime just sitting doing computations, right? Now the other challenge is whenever we assign multiple RUs, right, basically we are splitting up this 80 megahertz into smaller chunks of bandwidth and assigning them. There are so-called null tones or null subcarriers that are introduced. Okay, this is as per the RU plan. So the more you subdivide the 80 megahertz and make it smaller and smaller chunks, we will be losing a lot of subcarriers to these null subcarriers, which can't be used for sending data. So null tones reduce the data rate anywhere, actually from 5% to 18%, but a more typical number is like 12 to 18%. Okay, so this is a significant limiting factor of OFDMA, so that when we start itself, OFDMA starts with this 12% to 18% loss compared to single user, right? So in which case OFDMA will be beneficial only if the gains are exceeding that 18% loss, right? So to get a net gain, we have to compensate for this loss. Then thirdly, we have to get buffer status reports from the clients, right? So unless the AP knows the buffer status from all the clients accurately, it will not be able to schedule for the clients correctly. So the good thing is the buffer status reports do not have to occupy a lot of airtime because they are not separate frames. These buffer status reports can be included in the MAC header of any uplink frame, right? In the cost control or in the HD control fields, these can be included, right? So it doesn't incur separate frame overhead, but it can be piggybacked on existing uplink frames. But the point is clients have to provide this information. If the clients do not provide this information, then the AP will not be able to schedule properly, right? So these are all the pros and cons of the OFDMA. So let's do some calculation to understand in what scenario OFDMA will have gain. So first scenario we're going to take is a simple 20 megahertz bandwidth. AP is in 20 megahertz bandwidth. Let us assume the clients are all using an MCS of 7, right? And let's assume that the ACs are also obtained using OFDMA, right? So let's assume the MCS for the ACs is like MCS 3. Let's assume the number of users is 4 users. So 20 megahertz is split between 4 users. So that can be done with RU size 52. So we can assign RU 52 to each of the 4 clients, and we can transmit OFDMA. So let's, for the purpose of calculation, assume that the per user queue size is about 20,000 bytes. So basically there is 20,000 bytes of traffic to be sent by each of these clients, right? Now if we send this as single user, what will happen is, as I showed in this picture, there is going to be 4 transmissions, 4 SUPPDU transmissions, which means 4 times we will incur the random backoff overhead, and then 4 times we will incur the 5 header overhead, right? So which is kind of indicated in this plot here, where I have calculated the total airtime required to send all this payload to the AP, right? And I've split that total airtime into 3 parts. One is the time incurred doing random backoff, which is the blue color, and the time incurred to send the data. This includes the 5 header overhead as well as the payload data. And then finally, the orange color is for the ACK, right? This is the airtime occupied by the ACKs. Remember, in single user case, in the SU strategy, we have to send 4 different ACK frames, right? Whereas in the OFDMA case, these all are consolidated into this multi-star block ACK, right? So if you look at it, in this case, OFDMA in total consumes more airtime here. And why is that? Because the pink portion, that is the data portion, consumes a significantly higher airtime because the OFDMA data rate is lower than the single user data rate. So this is because of the null tones, right? So in this case, despite having a significant savings on the back off portion, right, there is a blue color, you can see there is definitely savings here. Despite those savings, the OFDMA is consuming more total airtime compared to the single user. In this case, OFDMA gain turns out to be negative. So clearly, this is the large payload airtime scenario, right, where the OFDMA consumes more total airtime and the gains are negative. Now let's look at the small payload airtime scenario, and for that example, I'm going to make one small change. Instead of 20 megahertz bandwidth, let us assume 80 megahertz bandwidth for the access point, right? So which means the data rates are now 4 times higher, which means for the same payload, which is 20,000 bytes per user, the payload airtime is going to shrink, right? It's going to be smaller, right? So we will be having a small payload airtime scenario, and in this case, instead of RU52, we can use RU242 for each of the users, right? And in this case, if we repeat the calculations, we see that OFDMA in this case consumes significantly lesser airtime compared to single user, right? Single user is taking about 1750 microseconds, whereas OFDMA takes only about 1300 microseconds, right? Now this is despite the reduced OFDMA data rate, right, compared to single user because of the null tones overhead, right? Still the gains are positive, right? So in the small payload airtime scenario, OFDMA is definitely beneficial, right? Now note that I have not even considered the savings that we get because of reduced collisions, right? So if you add the savings that you get in terms of airtime because of reduced collisions, the gains will be even more than what is showcased here, right? So, and if you have even higher bandwidth, like 160 megahertz bandwidth or 320 megahertz bandwidth, the OFDMA gains are likely to be even higher, because you're basically entering a territory where the payload is like significantly smaller and the phi header starts to become a dominating factor in the airtime calculations, right? Another point is, as you increase the number of users, right, we will have more OFDMA gain. That is because the collisions become a significant or dominating factor. So the more users that you have, OFDMA will tend to show much higher gains. Okay, so now we understand the OFDMA gains in theory, in what scenario we will see the gains, right? So what is the right metric to capture all these gains? So clearly from all these calculations, we can see that airtime, that is the total airtime consumed, looks like one of the good metrics to capture the OFDMA gains, right? So note that airtimes is the right metric. I think in my opinion, airtime is a better metric. I know some previous testing by various companies has used latency instead of airtime, but I think airtime is a much more powerful way to showcase the benefits. If you look at latency, right, latency depends on a lot of factors, right? If you look at end-to-end latency, there is scheduling latency, software also takes some CPU cycles, and then there is queuing latency. So I think showing gains in terms of latency in OFDMA is a little bit challenging, but showing gains in terms of airtime should be much simpler, and it's very straightforward, right? As we can see in theory, right? Again, this is all in theory. Now let's look at the practical challenges of demonstrating that airtime advantage of OFDMA. So how to test the OFDMA benefit? So clearly the test case should be that we run simultaneous uplink traffic from multiple clients, right? And we should be having the small payload airtime scenario, right? So we should have low uplink traffic to simulate this or create the small payload airtime scenario, and we should have multiple OFDMA capable clients connected to the AP and sending uplink traffic. So that's the test case. Now what should be the metric that we measure, right? So the metric should be, as we discussed, we should be measuring the total airtime utilized, right? And we should compare that for OFDMA disabled versus OFDMA enabled on the AP. So hopefully we have a knob, enable disable knob on the AP, where we can enable or disable the OFDMA and make this comparison. Okay, so that seems pretty straightforward, again in theory, right? So let's look at the practical challenges now, right? So first of all, it is complicated to measure the utilized airtime, okay, because there is all this interframe spacing, random backoff, act time, and all these things. So it's difficult to kind of measure the total airtime utilized, including all this interframe spacing, random backoff, act time, and all, right? So what is the alternative? How about we measure unused airtime instead of measuring the utilized airtime, right? Maybe measuring the unused airtime is simpler compared to measuring the total airtime, right? So that sounds like a good idea, but again, how do you measure this unused airtime, right? Now, there are no off-the-shelf test tools that are available on the market today, at least to my knowledge, to measure the unused airtime, okay? But we do have a lot of tools to measure throughput, right? For example, Candela itself has several tools, to help us measure the throughput, right? And there are many other vendors today which are providing tools to measure the throughput. So what if we can convert the unused airtime into an equivalent throughput and then make it a throughput measurement exercise, right? If we can successfully do this conversion, right, then we can use the throughput test tools to kind of infer the unused airtime, right? So that's the key idea of this presentation, right? The solution or my proposal to how to do that is introduce another non-OFDMA client into the mix and run unlimited uplink traffic on it. So basically you have a bunch of OFDMA capable clients, right, which are going to be served with OFDMA, and then introduce another non-OFDMA client, and on that client we should run unlimited traffic on it. To the OFDMA clients we should be running that small payload airtime, right? So we should have low uplink traffic, and then on the non-OFDMA client we should have unlimited uplink traffic, which means any unused airtime which is left over by the OFDMA capable clients will be utilized by this non-OFDMA client, right? Which means the throughput that this non-OFDMA client achieves is a direct measure of the unused airtime, right? So here we got a nice method where we can kind of indirectly measure the unused airtime by measuring the throughput of this non-OFDMA client. So that is the key idea of this presentation, right? And hopefully you got the the idea here. Now let's go to the test results. So here is my proposal, but we also went one step further, and I'm going to present some results also that have been captured using this idea presented here. And for this, I should thank Candela Technologies, because Srisha, along with her team in Candela, helped do this testing as per the test case that I described, and this was done in a very short notice. So thanks to Srisha and her team, and also Sitarama sir for helping and supporting in this exercise. So here are the test results. So by the way, this is all Srisha put together all this, so thanks to her. So here is the test topology, okay? And we can see 15 clients here. So totally we had 15 clients, a mix of several types of OFDMA capable clients, mostly the BE200, which is the Intel BE200, which is a Wi-Fi 7, and then there was a AX210, which is a Wi-Fi 6E, and then there's a Samsung Galaxy S20, which is a Wi-Fi 6. Okay, so mix of Wi-Fi 6, Wi-Fi 6E, and Wi-Fi 7 devices, and there is also an 11 AC client in the mix. So this is the non-OFDMA capable client that we used. So this will not participate in the OFDMA, right? And we are going to run unlimited uplink traffic on this 11 AC client, whereas with the remaining 14 clients, we will be running very little traffic. In particular, we are going to be running 1 Mbps traffic, uplink traffic for all the 14 clients. So 14 Mbps in total, right? So 1 Mbps each. So totally 14 Mbps in total across the 14 clients, right? Now, the AP that we used, okay, so here is the testbed image, okay? So this is how the setup was put together. So all the clients were at short range from the AP, right? So it was all inside a shield room, right? Now, here is the details of the clients, right? And we've also provided the driver version that was used for the Intel BE200, right? And here are the AP details. So the AP that was used was an ASUS GT AX 6000 AP. This is a Wi-Fi 6 4x4 AP, and this was set to 80 megahertz bandwidth, and the testing was done in 5 gigahertz. So the traffic profile that was run was to all the 14 OFDMA clients. We ran UDP uplink 1 Mbps traffic, and this was using voice access category. Okay, so we are basically trying to simulate kind of voice traffic, and the payload size that was used was 700 byte frames. So 700 byte frames with a throughput of 1 Mbps per client, right? So totally 14 Mbps across the OFDMA, 14 OFDMA clients. And then we had the Wi-Fi 5 client, right? That's 11 AC client. We were running full load UTB uplink. This was using best effort traffic at 1500 byte payload size. Okay, so that's the traffic profile. Now let's look at the results. So these were the client side metrics that were captured just to confirm that all the clients connected at 80 megahertz, and then the RSSI that was seen on, at all the clients, and they are all 2x2 clients, right? So here are the results with OFDMA disabled on the AP. So we did have a knob on the ASUS AP to enable or disable OFDMA. So this is the throughput that is seen by the Wi-Fi 5 client, right? And this is the throughput that is seen by the 14 OFDMA clients together, right? So 14 Mbps. So we should see about 14 Mbps, which we do see here, right? About 14 Mbps for the OFDMA capable clients, and this throughput for the Wi-Fi 5 client is a measure of the unused airtime, right? So, and it's seeing somewhere about 100 Mbps. There are some spikes which take it to like 350 Mbps maximum, right? But it is not able to sustain it, right? Later I will tell you why that is happening, or what we observed here, right? It's basically it's not very stable. There are some spikes like this, but you can see the average throughput is around 110 Mbps, I think. Now the same test when repeated with OFDMA enabled looks like this, right? So we are seeing about 500 Mbps throughput for the Wi-Fi 5 client, and still we do see the same 14 Mbps throughput for the OFDMA cable client. So the traffic to the OFDMA cable clients is going as normally and without any disruption, while the Wi-Fi 5 client is able to now achieve a significantly higher throughput. So this clearly shows that now the OFDMA traffic is consuming much lesser airtime. So there is more airtime available for the Wi-Fi 5 client to use, and that is seen by the throughput. Right? And we also, by the way, confirmed that OFDMA is actually happening, right? In multiple waves. We were able to look at some counters from the AP to infer how many trigger frames are being sent, and we also actually use a sniffer to capture the basic trigger frames, and here is a sample of the basic trigger frame that was captured. So here we can see RU242 being assigned to 4 different clients here, right? So OFDMA is actually happening, okay? Now here is a summary of all the results put together. So OFDMA disabled, we got about 110 Mbps. OFDMA enabled is about 540 Mbps. The throughput to all the OFDMA cable clients pretty much stays the same, which is 14 Mbps. So that brings me to the end of this presentation. So hopefully you got a good idea about how to measure the OFDMA gains, and we can hopefully put a full stop to this question of whether there is OFDMA gain or not, right? We do see significant OFDMA gains, as you can see from the results here. Now one thing I would like to say is, please don't try to look for this exact multiple of gain, like this looks like 4 times throughput, right? When you try to repeat this test, maybe you might see lesser gain, but definitely you will see gains. I think that the key takeaway is not that there is OFDMA gives 4 times throughput or 5 times throughput. The key message is that there is benefits with OFDMA, right? And it's just that we have to craft the right test case and use the right test tools to see that gains. Now, one final remark about why this OFDMA disabled throughput is not very stable here. So one thing is on post-processing all the logs from the sniffers and all. What I could observe is that the OFDMA capable clients are definitely experiencing quite a bit of collisions. Now note that this is all voice access category, right? And as you know, voice access category has aggressive context window parameters. So they do experience a lot of collision, and that is causing the rate adaptation on these clients to kind of reduce the rate, and we could actually see that from the sniffer logs. So that is why you see this instantaneous spikes going up to 350, right? But it's not able to sustain it because very quickly it sees a lot of collisions, and then that causes the rate to kind of stumble, right? So the rate adaptation is really basically causing these fluctuations. Okay, so basically because of that, the airtime utilized is kind of fluctuating quite a bit, and that is reflected in the throughput for the Wi-Fi 5 client. Okay, so that's a little insight I wanted to share. Whereas you don't see this behavior, we didn't see this behavior in the OFDMA enabled case. We could see that the rates were pretty stable, right? The collisions also we could see were significantly reduced. Okay, thank you for your time.